this is a quick recap of chapter gravitation. So let's start with gravitation and gravity. Gravitation is the force of attraction between any two bodies, while gravity refers to the force of attraction between any body and the earth. Newton's law of gravitation. It states that every body in this universe attracts each other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, F will be equals to G m1 m2 upon r square, where this capital G is the universal gravitational constant. It was derived by the Newton on the basis of the Kepler's law of planetary motion. Universal gravitational constant, that is capital G. It is equal to the force of attraction between two bodies of unit mass each and are separated by unit distance. In SI units, G is equals to 6.67 into 10 to the power minus 11 Newton meter square per kg square. And in CGS unit, G is equals to 6.67 into 10 to the power minus 8 dyne centimeter square per gram square. The dimensional formula of G is m to the power minus 1, L to the power 3 and T to the power minus 2. Now, properties of gravitational force. The gravitational force between two point masses, first is independent of intervening medium. Second, it obeys the Newton's third law of motion. Third, it has a spherical symmetry. Fourth, it is independent of the presence of other bodies. Fifth, it obeys the principle of superposition. Sixth, it is conservative and central force. Now, principle of superposition of gravitational forces. The gravitational forces between two masses acts independently and uninfluenced by the presence of other bodies. Hence, the resultant force on a particle due to a number of masses is the vector sum of the gravitational force exerted by individual masses on the given particle. We can say Fr vector will be equals to F1 plus F2 plus F3 up to Fn, and this can be written as in this summation form. Summation Fi where I is equals to 1 to n. Next is shell theorem. First, the gravitational force on a particle placed anywhere inside a spherical shell is 0. Second, if a particle lies outside a spherical shell, the shell attracts the particle as though the mass of the shell were concentrated at the center of the shell. Now, free fall. The motion of a body under the influence of gravity alone is called free fall. Acceleration due to gravity, which is represented by small g. The acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity. At the surface of the earth, G is equals to G m upon r square, where this m is the mass and r is the radius of earth. It is a vector quantity. The SI unit is meter per second square. Mass of earth. It is given by m is equals to small g capital R square upon capital G. Now, mean density of earth. It is given by m will be equals to g R square upon G. So, if the earth is a sphere of mass capital M and mean density rho, then its mass would be volume into density, which will be equals to 4 by 3 pi r cube into rho. And also this can be represented at G r square upon G. Therefore, we can say 4 by 3 pi r cube rho will be equals to G r square upon G, and then rho will be equals to 3G upon 4 pi G r. Now, next is weight of a body. It is the gravitational force with which a body is attracted towards the center of the earth. W will be equals to mg. Weight of a body is a vector quantity. It is measured in Newton, kg, watt, etc. The weight of a body varies from place to place because of the variation in the value of small g. Now, variation of acceleration due to gravity. First is effect of altitude. At height h, gh will be equals to g in the bracket 1 plus h upon r minus 2 power, and gh is equals to g into 1 minus 2h upon r when h is less than r. Clearly the value of g decreases with the increase in height. Second, effect of depth. G at a depth d, gd will be equals to g 1 minus d upon r. Clearly the value of g decreases with the increase in the depth d and becomes 0 at the center of earth. Third is effect of rotation. If omega is the angular velocity of the earth about its axis of rotation, then at latitude lambda, g lambda will be equals to g minus r omega square cos square lambda. As lambda increases, cos lambda decreases and g lambda increases. So we move from equator to pole, the value of g increases. At equator, lambda is equals to 0 degree, then cos lambda will be equals to 1, then this g at equator will be equals to g minus r omega square. At poles, lambda is equals to 90 degree, cos lambda will be equals to 0, then g at pole will be equals to g minus r omega square into g will be equals to small g. Hence g is minimum at the equator and maximum at the poles. G pole minus g at equator will gives r omega square. And the last one is effect of non-sphericity of the earth. The earth has an equatorial bulge and is flattened at the poles. As RE is greater than RP, so the value of G is minimum at the equator and maximum at the poles. Now let's move towards gravitational field. It is the space around a material body in which its gravitational pull can be experienced by other bodies. Now, intensity of gravitational field. The intensity or the strength of gravitational field at any point in a gravitational field is equal to the force experienced by a unit mass placed at that point. It is a vector quantity directed towards the body producing the gravitational field. It is given by E will be equals to force upon mass will be equals to gm upon r square. The intensity of gravitational field at a point is equal to the acceleration due to gravity at that point. The SI unit of this intensity of gravitational field is Newton per kg, and in CGS the unit is dyne per gram. Now, gravitational potential. The gravitational potential at a point in the gravitational field of a body is the amount of work done in bringing a body of unit mass from infinity to that point. It is a scalar quantity. Gravitational potential V is equals to work done upon mass, which will be equals to minus G capital M upon R. The SI unit of gravitational potential is joule per kg and CGS unit is erg per gram. Now, gravitational potential energy. The gravitational potential energy of a body may be defined as the energy associated with it due to its position in the gravitational field of another body, and is measured by the amount of work done in bringing a body from infinity to a given point in the gravitational field of the other body. Gravitational potential energy will be equals to gravitational potential into mass. So we can say that U is equals to minus G capital M upon R into M. Gravitational intensity and gravitational potential V at a point are related as E is equals to minus dV upon dr. Now next is escape velocity. It is the minimum velocity with which a body must be projected vertically upward in order that it may just escape the gravitational field of the earth. V equals to under root 2 g m upon r. which can be written as under root 2g capital R. For Earth, the value of escape velocity is 11.2 km per second. It is independent of the mass of the body projected. Now, next topic is satellite. It is a heavily or an artificial body which is revolving continuously in an orbit around a planet. Next topic is orbital velocity of a satellite. VO. It is the velocity required to put a satellite in its orbit around a planet. The orbital velocity of a satellite revolving around the Earth at a height h is given by VO will be equals to under root gm upon r plus h will be equals to under root g r square upon r plus h will be equals to r under root g upon r plus h. When a satellite revolves close to the surface of Earth, we can say that h will be equals to 0. P naught will be equals to under root gr and VE will be equals to under root 2 V naught. Now next is time period of a satellite. It is the time taken by a satellite to go once around the planet. It will be equals to circumference of the orbit upon orbital velocity, which can be written as 2 pi and the bracket r plus h upon V O will be equals to 2 pi r plus h upon under root gm upon r plus h will be equals to 2 pi under root r plus h whole cube upon gm will be equals to 2 pi under root r plus h whole cube upon gr square, and finally this will gives under root 3 pi r plus h whole cube upon g rho r cube. If the satellite revolves just close to the surface of the Earth, h equals to 0, then t will be equals to 2 pi under root r cube upon gm. It will be equals to 2 pi under root r upon g equals to under root 3 pi upon g rho. Now, height of a satellite above the Earth's surface. We know that t is equals to 2 pi under root r plus h whole cube upon gr square, or we can say that r plus h whole cube will be equals to t square r square g upon 4 pi square. From this equation we can calculate the height. H will be equals to in the bracket t square r square g upon 4 pi square to the power 1 by 3 minus r. Now, angular momentum of a satellite. The angular momentum of a satellite of mass m moving with velocity VO in an orbit of radius r is equals to r plus h is given by L will be equals to m naught VR equals to m in the under root gm upon r into r equals to under root gm small m square r. Now, total energy of a satellite. For a satellite of mass m moving with velocity VO in an orbit of radius r, the potential energy U will be equals to minus g capital M small m upon r, and kinetic energy will be equals to half m V naught square will be equals to half m into gm upon r, and total energy is the sum of potential energy and kinetic energy. So on summing on adding these two, we get minus gm upon g capital M small m upon 2r, and clearly we can define as total energy will be negative of kinetic energy will be equals to half of potential energy. Now, geostationary or synchronous satellite. It is the satellite which revolves around the Earth with the same angular speed and in the same direction as the Earth rotates about its own axis. Such a satellite should revolve around the Earth from west to east in an orbit concentric and coplanar with the equatorial plane of the Earth at height of 36000 km. Three geostationary satellites with a mutual angular separation of 120 degree can be used to communicate between any of 2 points on the entire Earth. Now, next is polar satellite. A satellite that revolves in a polar orbit is called polar satellite. Such a satellite passes once over geographical north and south poles during each round trip. A polar orbit has a smaller radius of 500 to 800 kilometer. Now, next is conservation of quantities in motion under gravitational influence. During the motion of an object under the gravitational influence of another object, the following quantities are conserved. First is angular momentum, second is total mechanical energy. Linear momentum is not conserved. Conservation of angular momentum leads to Kepler's second law of planetary motion. Now let's discuss Kepler's laws of planetary motion. First, law of orbits. Every planet moves in an elliptical orbit around the sun, with the sun being at one of the foci. Second law is law of areas. The radius vector drawn from the sun to the planet sweeps out equal areas in equal intervals of time. For instance, the aerial velocity of a planet is constant. Third and last law is law of periods or harmonic law. The square of the period of revolution capital T of a planet around the sun is proportional to the cube of the semi-major axis r of the ellipse. Here you can see. Next is weightlessness. A body is said to be in the state of weightlessness when the reaction of the supporting surface is zero or its apparent weight is zero. An astronaut experiences weightlessness in a space satellite. This is not because the gravitational force is small at that location in the space. It is because both the astronaut and the satellite are in the state of free fall towards the Earth. Next is inertial mass. The mass of a body which measures its inertia and which is given by the ratio of the external force applied on it to the acceleration produced in it along a smooth horizontal surface is called inertial mass. The formula for inertial mass will be equals to applied force upon acceleration produced. Now, the last topic is gravitational mass. The mass of a body which determines the gravitational pull due to the earth acting upon it is called the gravitational mass. On the surface of the earth, F will be equals to G capital M small g upon R square. And therefore, gravitational mass small mg will be equals to Fr square upon Gm. Inertial mass of a body is equivalent to its gravitational mass. Thank you.